And our next speaker is Hassene, Aissi.
Yes.
Please share your screen.
Can you see my screen?
Yes, I can see it, and I can hear you. So Hassene will talk about faster algorithms for next breakpoint and max value for parametric global minimum cuts. Please.
Thank you for the introduction. So this talk will deal with parametric version of the global min cut problem. This is joint work with Tom McCormick and Maurice Keiram from the Soder School of Business and UBC. I will define two parametric global min cut problems, and then I will give deterministic and randomized algorithm to solve them. Let's define the problems. Given a directed graph, J, with n nodes and n edges and non-negative edge costs, a global cut is induced by a non-trivial subset of nodes C, different from the trivial set, empty set, and the whole node set V, and includes a set of edges, delta C, which have exactly one end in C. So we'll consider that the cost of of a cut is the summation of the costs of all the edges in delta C. In this talk, we will be interested in the running time of several algorithms. So let me remind the best deterministic and randomized algorithms to solve the standard global min cut or the non-parametric min cut. So here are the best deterministic algorithm given by Storer and Wagner, or Nagamoshi and Ibaraki. It is in order of mn and plus n squared log n. And for the randomized algorithm, there is a Karger-Stein algorithm which runs in O tilde n squared, which was later improved by Karger in almost linear time of order m. An interesting property of the global min cut problem is that there is a strongly polynomial number of approximate min cuts. By alpha approximate, we mean that the cost is alpha times the optimal value. And these approximate min cuts can be computed also in strongly polynomial time, either using a deterministic algorithm or a randomized algorithm. And this property will be very useful for us in order to get a fast algorithm to solve one of the parametric problems. So in the rest of the talk, I will deal with parametric costs. So here we'll consider the case where the edges have parametric costs. More formally, we have d plus one edge cost function, C node until CD. And the cost of each edge, E, is an affine function of the parameters mu I, as shown in this formula. It is common in parametric optimization that to not impose that all the cost function Ci to be non-negative, because in some contexts, some property may improve by increasing the mu I value, and some other property may decrease. So in general, we have non-negative, we have unrestricted insign edge cost function Ci. But in order to avoid the NP hardness, we assume that all the edge costs belong to a polytope where the edge costs are non-negative. So it is an intersection of all the edge costs where C mu of E is non-negative. So why it is interesting to consider global parametric global min cuts? Because in some situation, we have that the edge costs may vary because of external variables. Think of mu I and the cost Ci. Also because in other contexts, we can model the problem of attack and defense on graphs. So we have a defender who can spend a fixed amount of budget on D resources in order to reinforce the edges of the graph against an attacker. We will be interested in the minimum cut value when we vary all the parameters mu. So it is a parametric function. And since this function z, let's call it z of mu, is the minimum of many affine functions, one associated to each cut in the graphs. So this function z is piecewise linear and concave function. A nice property of this function z is that it has a strongly polynomial number of facets, which are linear parts of this, the surface of z, and also it has a strongly polynomial number of breakpoints. And this surface z can be computed in strongly polynomial time. But in the particular case where all the edge cost functions ci are non-negative, the number of facets and the running time can be improved significantly. And this was a result by Kerger in 2016. So computing the whole surface Z is good, but maybe too much for some applications. In this talk, we will consider a more narrower subjects where we don't need, in fact, to compute the whole surface. So let me define the problems that we are concerned with. So the first problem is the next breakpoint. So we have a parameter mu node, a direction, and we would like to find, as shown in the picture below, the next breakpoint in a given direction after the starting point mu 0. So this breakpoint may exist, and we would like to compute it if any. The next problem that we deal with is the maximum problem. So we would like to find the point mu star where the function z reaches its maximum, as shown in this figure. The next breakpoint problem corresponds to the ray shooting problem, which is a standard topic in sensitivity analysis in order to identify ranges where the optimality is preserved and other related quantities. Clearly, the next breakpoint problem in contrast with the maximum problem is a one-parameter problem. So we can rearrange the costs in such a way that we obtain parametric costs which depend on only a single parameter, let's call it lambda. So it gives the impression, the first impression, that the next breakpoint is maybe simpler than solving the maximum problem. For the attack and defense problem, the attacker may only be interested in solving the maximum problem because the defender will find the point mu star where the function z reaches its maximum, because he would like to make the minimum cut value as big as possible. So we solve the max min problem for the attack and defense problem. Clearly, we could solve this problem by computing the whole surface, but the goal here is to get faster algorithms for this problem by using some structural result for the global mean cut in general. One way to solve this parametric problem is to apply the Megiddo's parametric framework, which is a very generic framework to solve parametric problems. So Megiddo and later with Cohen, they gave a framework to adapt linear algorithm for non-parametric problem, which means standard problem, in order to solve the parametric problems. So by linear here, we mean that in each step of the algorithm, comparison will be between two affine functions and the data, affine function of the parameter mu. So this is not a restrictive constraint because many standard combinatorial problems are in fact linear. In general, the Megiddo's trick introduces a slowdown with respect to the non-parametric algorithm. So in general, they are not optimal in the sense that they are tied with the best algorithm to solve the non-parametric problems. We show that the standard Stower and Wagner algorithm is linear, so this is not difficult. And therefore, by combining it with the Megiddo parametric framework, we can solve the max and the next breakpoint problem in strongly polynomial time. Note that for the max problem, the running time is exponential on the number of parameters, which is supposed to be constant, but you cannot do better than that. Because if the number of parameters is very big, so we expect that the problems are very hard. Tokoyama in another paper observed that the Karger-Einstein algorithm is linear. So again, by combining it with the Megiddo trick, he obtained a strongly polynomial time randomized algorithm to solve these two problems. Using Megiddo's tricks, we have the impression that the next breakpoint and the max problem can be have the same difficulty because they have the same running time if we fix the number of parameters to 1. So our goal here is to beat the general Megiddo approach by devising more specific algorithm to the global mean cut problem. So here is the summary of running time where we compare the non-parametric running times and the Megiddo's ones. Our hope to result is try to improve the Megiddo's algorithm and to obtain some algorithm which have running time lying between the lower bound times given in green, which correspond to the non-parametric algorithms, and the blue one correspond to the Megiddo's framework. So let me discuss the algorithm for solving the next breakpoint problem. Our deterministic algorithm will be based on the Stower-Wagner algorithm to solve the global mean cut. So in this algorithm, we compute an ordering of the nodes V1 until Vn, such that the last pair Vn minus 1 and Vn correspond to a pendant pair, which means that either the node singleton Vn is a global mean cut, or we can contract this this pair without losing any optimal cuts. In the parametric settings, we will consider at each iteration a contracted graph GR, and we will be interested in the function of the minimum cuts defined by the nodes of the contracted graphs. So this function Z of R is also piecewise linear and concave. And we will be interested in its intersection with the local slope at our starting point. So by the concavity of the mean cut function, which is piecewise linear and concave, as we said before, we can show that this intersection point lambda r gives an upper bound on the unknown next breakpoint. And so by using the concavity of this function, if we compute the ordering, maximum adjacency ordering of the Stower and Wagner algorithm using the cost defined by this lambda r, so we get at the end a pendant pair, and we can show that either the last node Vn correspond to the, define the cut associated to the next breakpoint, or we can contract this last pair without losing any cut defining the next breakpoint. So in terms of running time, computing the minimum of the cuts defined by the node can be done very quickly, and this running time is dominated by the running time of computing and ordering of the nodes. So our algorithms has the same running time as the Stower and Wagner algorithm. So in a sense, it is an optimal algorithm. So what is surprising is that the parametric problem has the same complexity as solving the standard global mean cut problem. In comparison to the Megiddo general framework, we solved a logarithmic factor. This is the best that we can do. Now for the randomized algorithm, we will rely on the Karger-Einstein algorithm in order to solve the next breakpoint. So the algorithm performs a number of random edge contraction. So at each step, we'll consider a contracted graph, and we will pick randomly an edge in this contracted graph proportional to its cost defined by some parameter lambda r. So what is important here is to select carefully this parameter lambda r in order to bound the error probability and to keep at the end an optimal minimum cut corresponding to the next breakpoint. So the random edge contraction sequence continues until obtaining at the end a graph with only 2 nodes. And we show that if the next breakpoint exists, then the remaining cut is optimal with high probability. Otherwise, the algorithm detects that there is no next breakpoint with probability 1. So the idea of the algorithm is has a geometric flavor. So define again the local slope L of lambda. And now we will compare it with an upper bound corresponding to the average cost of all the cuts induced by this node singletons. So we know that in the standard global mean cut, the optimal value is at most the average of the cost of defined by these nodes. So similarly, we have the same setting in the parametric context here. And we will be interested in the intersection of the black and red lines. So in fact, since any cut in the contracted graph corresponds to a cut in the original graph, so therefore this intersection point lambda r of the local slope and the upper bound cannot be between 0 and the unknown next breakpoint. So lambda r is again an upper bound of the unknown next breakpoint. So by using the concavity of the z function of the parametric mean cut value, so if imagine that we know the next breakpoint, so we can draw a third line corresponding to the cut defined the next breakpoint. So at lambda r, this unknown line, unknown facet, will be below the intersection of the red and the black lines at lambda r. So using this geometric observation, we can upper bound the error probability of picking an edge at each iteration to a quantity, to 2 divided by the number of current nodes, which is exactly the same bound as in Karger-Einstein. So therefore, we does not deteriorate the error probability, even though we have parametric costs. So if we combine this result at all the iterations of the algorithm, so we obtain the same error probability as Karger-Einstein, and therefore our algorithm is correct and have also the same running time as Karger-Einstein. So
you
in
have
a sense,
5 minutes. So you have 5 minutes left.
Yeah, thank you. So in a sense, our algorithm is optimal in comparison to Karger-Einstein. So let me remind here the running time in comparison to Megiddo. So we saved a logarithmic factor. So very quickly, let me move to the maximum problem. So the max problem, in a sense, is more difficult than the next breakpoint problem. So we'd like to use the same idea as memory and our previous result in order to compute this target value by using an approximate duality with the maximum spanning tree and the minimum cut in one hand, and also the ability to compute all the approximate minimum cuts in a strongly polynomial time. The relationship with the maximum spanning tree is relevant only when all the edge costs are linearly ordered. But typically, in a parametric context, the edge costs are only partially ordered. So this introduces a difficulty in comparison to the standard context. And also we need to perform a search and to find a narrow region containing the unknown target value. And in this narrow region, we will enumerate all the approximate cuts. And then among them, we can find our, we can compute our target value mu star. So for that purpose, we will use, we will borrow a technique from the computational geometry called point location arrangement to achieve this, this target. So here we have a set of hyperplanes, a polytope, and the target value, think of our mu star unknown value. And then by applying this PLA algorithm, we can find a non-empty simplex containing this target value. So our algorithm will call iteratively this geometric tool in order to find at the end a small region where we can, using the result of approximate cuts, where we, therefore we can compute our target value. So let me skip all these slides and go to the running time. So here we can compare our improved running times in comparison to Megiddo. So here the dependence on the number of parameters is only on the log part and not on the number of nodes. So Megiddo's algorithm is much slower than our algorithm because we use it a structural result of the global mean cut. And here we use the different techniques from for solving max problem and next breakpoints. So it suggested that the maximum problem is strictly harder than the next breakpoint. In contrast to Megiddo, we had initially the impression that these two problems have the same complexity. For the randomized algorithm, unfortunately, we can only improve the running time of Megiddo only for a single parameter. So it is an open question to get a fast randomized algorithm if we have a higher number of parameters. So as a conclusion, here is a summary of all the running times. So the new results are given in red, and you can compare it to all the previous running time. That's it for my presentation. So thank you for your attention. Any questions or comments?
Thank you very much. And yeah, we have time for questions. So please raise your hand. I have a question. Mm-hmm. So in this maximization problem, your constraint on mu was that the cost is non-negative, mm-hmm. right? But so suppose we have additional constraints on mu that it has to be in a polyhedron. Your algorithm still works for that case?
So if the edge costs are negative, so here the problem is that you consider the maximum cut problem, which is NP hard.
Yeah.
So for an NP hard problem, so
no, I mean
all this stuff will not.
Yeah, I mean it should be non-negative, but there are also some additional constraints on mu that so that mu is in some smaller. So you want to find the maximum in some smaller polyhedron, which is a subset of the polyhedron where the costs is non-negative.
Non-negative. So it can work. So we don't have any restriction on the size of the polyhedron. So the only condition is that to have non-negative edge costs.
I see.
Even in the parametric settings, and that's it.
Okay. Thanks.
Yes.
No hands raised yet.
I was trying to physically raise my hand. I have a question. So this Molly tool that you use, I think it is this hyperplane arrangement. So when you say that the target is unknown and you are able to find a simplex containing the target, obviously there must be some assumption. Is the separation oracle that you have, like you can find the hyperplane and you know which direction the unknown point is? It was in the previous slide that you had there.
Yes. So in fact, we borrowed the tool from computation geometry. So it is like in the Megiddo's parametric framework. So suppose that we have one dimension as shown in the slide here. So if you consider a point mu, we can test either the target value is on the right or on the left by computing the min cut. And you consider the slope. If it is increasing, so it is on the right, the maximum. If it is decreasing, so it will be on the left. And this geometric tool, in fact, generalized the binary search in higher dimension. So it is a standard tool that runs very quickly in order to guess, to compute a region containing a target value, even though you don't know that value.
Right, but my question is, how does this tool, what is the assumption? So for this tool, you don't know the value, but I presume that. So the assumption,
So in dimension 1, you only need to be able to compute a min cut. So if I take any mu, so there is no other further assumption.
Well, I guess you give me a point and you can find a hyperplane that either separate that point from the unknown point. Is that what the assumption that, that's the model. That's what I mean. Yeah, okay.
Okay, I see no other raised hands. So this is the last opportunity to ask questions. If there are no questions, then I unmute you all, and let's thank the speaker by a round of applause.